All right. So our next thing that we're going to be talking about, more asymptotes and more infinite limits. Last time we were looking at our graphs to figure everything out, but you might be saying, like, I don't want to look at graphs. So we're going to take a look at how we can figure out some of these limits that are going to infinity uh, without needing a graph. I thought I just played with my cat, but she doesn't think I played with her enough. Give her a treat and everything. So we're going to take a look at these two functions. First, she's playing with the laser over there, so that helps. So we've got sine of 2x over x. And what you notice is as this one is going to infinity, it's wobbling like sine does, but as it goes along, and you can pull it up down here if you'd like, as it goes along, it wobbles less and less and starts wiggling right above and below the x-axis. Okay, so we're back up and running. Sorry, everything crashed right there. So as this thing's wobbling around, it's heading towards zero. So that limit is just zero. Same thing on the other way. As we approach negative infinity, it's wobbling up and down above the x and y axis. I'm sorry, just the x-axis, not the x and y-axis. It's just wobbling towards zero. Since both of those are wobbling to zero, that creates a horizontal asymptote. So we do have a horizontal asymptote at zero. Now that sounds like counterintuitive because horizontal asymptotes is what it should approach, but not touch. That was kind of the old adage. More with these limits, the way we're going to be talking about them is it can cross a horizontal asymptote. It's just what it's approaching as it reaches infinity. Just like the other one with when we were shooting up and down, is what is it heading towards as it reaches infinity? Yeah, it never really touches it, but in terms of limits, we don't really care about where it is at zero. We just care about where it's heading towards. Now take a look at this other one. It doesn't have any horizontal asymptotes. It's just kind of like shooting up. So this one is just none. But I do want to point out just some characteristics about this graph. As we go to infinity to the right, it goes up. And so we get this nice big thing. And as we go to infinity towards the left, well, this way, as we head this way, it goes down. So as we're heading towards positive infinity, we're getting towards infinity. And as we head towards negative infinity, we go towards negative infinity. And the thing I want to point out, the reason that it's kind of doing this is because we've got an x cubed on the top. So if you think about, if you jam a really big number in there and you cube it, it's way big. And it's way bigger than anything on the bottom. So the number on top is way bigger because it's cubed than the number on the bottom. So that's going to produce a really big result. Think about what's happening over here. Sine is just wobbling in between 0, -1, and 1. So it's staying a very small number between -1 and 1. Meanwhile, as we approach positive infinity, we put this huge number in the denominator. It's so big. So we've got 1 over a big number. Well, that's 0. 1 over x, that's like kind of going closer and closer towards 0. So we're just getting smaller and smaller because that denominator is just muscling out the numerator, as opposed to this one where the numerator was muscling out the denominator. And that is going to be our key for evaluating these limits by hand, is comparing the numerators and denominators. Good time to pause. Oh, cat! I don't know, I'm just trying to give you a cool thing to pause at. So if the numerator, the degree of the numerator is less than the degree of the denominator, it's going to head towards 0 because who's going to win? And if the denominator wins, it's going to produce a really small number. If the numerator wins, then we get a huge number and it goes to infinity. If they tie, what ends up happening is you create a horizontal asymptote, and that horizontal asymptote is going to be the coefficients. And we'll do an example so we can see that in action. So here I've got a cubic and a squared. So if I think about this thing, the degree of this thing, the degree of my numerator, so 3 is bigger than 2. Since the numerator is bigger than the denominator, the numerator is going to win out. And so this limit of f of x as x goes to infinity is going to head towards infinity because the numerator is going to win. as opposed to down on this second example, 3 is smaller than 4. So the denominator in this case is going to win out because there's more denominator than there is numerator. So for this one, as x approaches infinity, f of x, these are h of x's. H of x ends up equaling 0. Now, the one in the middle, you can see those two cubes, in some sense, cancel each other out. So we look at, since 3 equals 3, we look at their leading coefficients. So we have a 5x cube and some garbage and an x cube. So the limit is going to be a ratio of those leading coefficients of that 5 and 1. So as x goes to infinity, h of x, it's just the two numbers. So 5 over 1, which is just 5. If there was extra stuff like a squared, a squared term and an x term, like I don't care about the 3. All we care about is those leading coefficients, because that cubes are going to knock out anybody else because they're just too big and too powerful. So they'll kind of like take control of the function. And what if we have this big boy, this big mess of stuff? We can't do direct substitution, remember, because we can't just plug in infinity. But it's just, what is this big number going to be? So since we got all this stuff, let's try to put it all together in one big polynomial and then check what those leading coefficients, what those leading degrees are. So I got to multiply all this stuff together. To do that, I'm going to take that 2 and I'm going to get that a common denominator with the x plus 1. Minus everything else. This parentheses is real small. And this garbage, I'm just going to leave alone, so I'll just put a squiggle. So we get 2x plus 1 minus x. So 2x minus an x, that's x plus 2 over x plus 1. I don't know why I put a parentheses there. And we still have our x squared and our 5 plus x squared. Need a little more space. So this is still y. So now in our numerator, we're going to multiply this by these two things. So we get x cubed plus 2x squared. In that denominator, we got a FOIL. So we end up with x cubed plus x squared plus 5x plus 5 plus 5. Okay, so now I check those leading coefficients. So my leading coefficients are 1. So, well, they're the same. So the degrees are the same. Do that first. Since our degrees are equal, we know that these things are going to kind of neutralize each other. So it's not going to go to infinity. It's not going to go to 0. We need that ratio. So we look at the limit of this over that. So it is 1. So 1 over 1, which is just 1. And that's going to be true for both positive and negative cases. So here, I'll just reset it, this page, so you can like see my nice handwriting a little bit faster. But for both positive and negative infinity, we don't have to do anything differently. Positive infinity, it's going to go to 1. Negative infinity still goes to 1. Doesn't matter if it's a big positive number or a small positive number, still going to go to 1. All right, now this one is a bit of a mess. I'm going to get my key here. So we don't have that nice polynomial thing, so we're not able to compare the ratio. So they gave us the hint to set it up and rationalize the numerator like we did a couple times ago. And then we can use our graphing utility to verify. So this should head towards 0. So whatever we end up with, we want to make sure that the denominator should end up winning. So let's multiply this. Let's get that pretend it has a denominator of 1, and we are going to rationalize our numerator. So I'm going to copy it and replace the thing in the middle with a minus instead of a plus. Note that I didn't do that inside of the square root. That stayed the same. So on my numerator, I just square those two terms. So I get x squared minus that whole stuff squared. So x squared plus 3. All over that new denominator I made, which is x minus the square root of x squared plus 3. Now we take a look at x squared minus x squared. Well, that's 0. And we just have a 3 in the numerator. And then in our denominator, we have, pen, please, x minus the square root of x squared plus 3. Now, if you look at all that stuff, so that's something that we can actually find the limit of. So this is the limit. Cannot remember my limits. Do not forget them. The AP Calculus test will not forget them. So our limit as x is approaching negative infinity, what's happening there is we have a mismatched. So the numerator has a degree of 1. Sorry, the denominator has a degree of 1. The numerator has a degree of 0. Since the denominator is bigger than the numerator, the denominator wins out, and so we head towards 0. So our limit should be 0. And once again, we can already see that in our graph. This thing is shooting down towards the x-axis. I'm getting that nice horizontal asymptote, right? Yeah. And that's it. That's it. So it's a big page, but just remember, if the numerator is less than the denominator, the limit goes towards 0 as it goes to infinity. If they are the same, then you need to take a ratio. And if the numerator is greater than the denominator, then it goes to positive or negative infinity. That's it for these limits. Bye.